The concept of time is something we all take for granted, with the ticking of the clock serving as a reliable constant in our daily lives. Yet, modern physics increasingly suggests that our understanding of time may be fundamentally flawed. Imagine for a moment that everything you thought you knew about time is not just incomplete but possibly an illusion created by the peculiarities of quantum mechanics. This idea, radical as it seems, is not just speculative, it is the basis of recent scientific research that has captivated physicists worldwide. The notion that time might be an illusion forces us to confront a deeply unsettling question: if time is not real in the way we think, then what is it? Could it be that time is merely a byproduct of quantum entanglement, a mysterious phenomenon in quantum mechanics? And if so, what does this mean for our understanding of the universe, our lives, and even the nature of existence itself? To appreciate the gravity of this idea, it helps to look at the history of scientific thought on time. Time, as we experience it, is a sequence of events moving in a single, irreversible direction, from past to future. This perspective aligns with what we call classical physics, rooted in Newtonian mechanics and furthered by Albert Einstein's theories. Newton viewed time as an absolute entity, constant and unchanging, much like an arrow that travels in a straight, predictable line. Time, in this classical sense, is something that moves at a steady pace, unaffected by the environment. Einstein, however, challenged this notion, proposing that time is relative rather than absolute. In his theory of relativity, time is interwoven with space to create a four-dimensional fabric known as spacetime. In this model, time can bend, slow down, or speed up depending on factors like gravity and velocity, thus behaving more like a river that flows with varying speeds and directions rather than an arrow on a fixed path. Einstein's relativity was revolutionary because it revealed that time is not as rigid as we once thought. However, even Einstein's framework does not capture the complete nature of time, particularly at the quantum level. Quantum mechanics is a branch of physics that explores the behavior of particles at microscopic scales, where the conventional rules of classical physics break down. Quantum mechanics introduced phenomena that defy intuition, such as superposition, where particles can exist in multiple states simultaneously, and quantum entanglement, where particles become linked in such a way that the state of one particle instantaneously affects the state of another, no matter the distance between them. It was Einstein who famously called entanglement spooky action at a distance, as it seemed to contradict the principle of locality, which holds that objects are only directly influenced by their immediate surroundings. In the realm of quantum mechanics, however, this principle does not apply in the same way. One of the most famous thought experiments related to quantum mechanics is Schrödinger's cat. In this scenario, a cat is placed in a sealed box with a vial of poison that could be released at any moment. Until the box is opened, the cat is both alive and dead, existing in a superposition of states. This paradoxical situation underscores the strangeness of quantum mechanics, where objects can exist in multiple states until they are observed. This phenomenon is closely related to the idea of measurement in quantum mechanics, where the act of observing a particle causes it to choose a state, collapsing from multiple possibilities into a single outcome. Quantum entanglement, however, takes this concept a step further. When two particles become entangled, their states are interdependent, meaning that a change in one particle's state will immediately affect the other, regardless of the distance separating them. If one particle chooses a state upon observation, the other will instantaneously assume the complementary state, even if the two particles are light-years apart. This defies our everyday understanding of time and space, as it implies that information can be transmitted instantaneously, faster than the speed of light, which is supposed to be the ultimate speed limit in the universe. While entanglement seems almost magical, it is a well-documented phenomenon that has been verified through numerous experiments. In recent years, researchers have proposed that time itself could emerge from the process of quantum entanglement. This theory, published in Physical Review A by a team of scientists from the Italian National Research Council, suggests that time may not be a fundamental aspect of the universe but rather a product of entangled particles. In other words, time could be an emergent property, arising from the interconnectedness of particles rather than existing independently. This idea is revolutionary because it challenges our foundational assumptions about time, suggesting that what we experience as the flow of time is merely the result of quantum relationships. To understand this theory, consider the way quantum mechanics treats time. In quantum physics, time is seen as an external parameter, a background that remains unchanged while particles move through different states. However, quantum systems themselves do not experience time in the same way. They exist in a kind of timeless state, with time only becoming apparent when we observe changes in a system. This view of time stands in contrast to Einstein's theory, where time and space are intertwined. The tension between quantum mechanics and relativity has been a source of great mystery in physics, leading scientists to seek a theory that can reconcile these two seemingly incompatible views. The researchers explored a concept known as the Page-Wouters mechanism, which suggests that time only emerges when one object becomes entangled with another that acts as a clock. According to this model, if a system is not entangled with an external object that can serve as a reference, it perceives the universe as static and unchanging, without a sense of time. In this way, time is not an absolute feature of the universe but rather something that comes into being through the process of entanglement. In experiments simulating this mechanism, researchers used a vibrating quantum oscillator and a group of tiny magnets as a clock. By entangling these systems, they observed that the behavior of the particles could be described by Schrödinger's equation, the fundamental equation of quantum mechanics, without needing to invoke time as a separate factor. As they expanded their calculations to larger, macroscopic systems, the researchers found that the equations began to resemble those of classical physics, where time behaves as we typically understand it. This finding suggests that time, as we experience it, may be a large-scale manifestation of entanglement, applicable even to objects we interact with daily. This perspective aligns with the idea that quantum physics underpins all of reality and that classical physics is an emergent phenomenon that appears at larger scales. If this is true, then our perception of time is a kind of illusion, a byproduct of the entangled states of the particles that make up our world. While the implications of this theory are profound, they are not without controversy. Many scientists remain cautious, noting that while the math may be consistent, there is no guarantee that the concept of time as an emergent property will lead to a unified theory that merges quantum mechanics with relativity. Nevertheless, this theory opens up exciting possibilities for rethinking the nature of time and its role in the universe. Even theoretical physicists like Michio Kaku have speculated about the implications of our evolving understanding of time. Kaku suggests that time, much like a river, could split into different streams or even form loops, making time travel theoretically possible within the framework of relativity. According to Kaku, if time behaves like a flexible fabric, we might one day be able to bend it into new shapes, potentially enabling backward or forward travel through time. However, such a feat would require an enormous amount of energy, far more than anything currently available on Earth. Kaku speculates that a civilization capable of time travel would need to harness the energy of an exploding star, a feat far beyond our current technological reach. Kaku also addresses the classic paradoxes associated with time travel, such as the grandfather paradox. If you were to travel back in time and prevent your grandfather from meeting your grandmother, would you erase your own existence? He offers two possible solutions: self-consistency, where natural laws prevent paradoxes from occurring, and the multiverse theory, where any changes in the past create a parallel timeline rather than altering the original one. In this view, any attempts to change the past would create a new branch of reality, leaving the original timeline intact. As we explore the mysteries of time, space, and the universe, Space Lab is here to take you on a journey through the latest discoveries, the most mind-bending theories, and the wonders of the cosmos that challenge everything we know. Thank you for joining us on this adventure into the unknown. There's so much more to uncover, and we can't wait to dive deeper with you. Don't forget to subscribe, hit the thumbs up, and stay tuned for more awe-inspiring content that brings the universe closer to you.